Hello and welcome to the next video. Random variables and their distributions. Okay, these are always shown as capital letters in textbooks. These random variables, a variable usually represents a number that we don't know yet, or that is something that we have to solve. But a random variable represents all the possible outcomes of a random experiment as well as the probabilities. It represents the whole thing, all possible outcomes. And to distinguish the individual outcomes, we use lowercase letters. So lowercase letters are single numbers, the individual outcomes of the experiment, but the capital letter represents the entire thing. It's a small but important point to make because you'll see these symbols used in the book and in my notes and other places. Okay, let's do a fairly simple example. If you flip two coins and define X, and that's capital X, as the number of heads you get, then we gotta think about all the possible outcomes and their various probabilities. So flipping two coins, it's possible to get anywhere between 0 and 2 heads. 0 is the minimum number, 2 is the maximum number, and it's also possible to get 1. So to complete the distribution, we have to find the probabilities of these various outcomes. So the probability of getting 0 heads, well, there's one way to get that, so that's 1 out of 4. The probability of getting 1 head, there's 2 ways that can happen, so 1 out of 2. And 2 heads, only one way that can happen, so probability is 1 out of 4. And that's the complete distribution, and that is the random variable X. And the probabilities have to all add up to 1. That's an important aspect of distributions, and that lets you know it's complete. You're finished if the probabilities all add up to 1. Okay, another example, it's a little bit larger. You're going to roll 2 dice, and X is the sum of the 2 numbers. Okay, so there's 36 possible outcomes of rolling 2 dice. And this is a table much like the last one I showed you. It shows the 36 possible combinations. But this has an added benefit. The little number there in red is the sum of the 2 numbers, so you can easily see the different sums. Okay, so out of the 36 possible outcomes, you just have to count how many ways there are to get the various outcomes. So looking from the smallest possible value first is 2, and there's one way to get a 2. Then 3, there's 2 ways that can happen. Then there's 4, that can happen 3 ways. 5 can happen 4 ways, and so on. You can go, you see the pattern is these diagonal lines going through the chart. So if you keep going through the entire chart, you get all your probabilities and count them up, and you'll get this distribution. 2 is the smallest possible number. 12 is the biggest possible number for the sum. And these are all their probabilities. You can see that the probabilities increase until you reach 7. 7 is the most likely. And that's because there's 6 different ways you can make a 7 from those numbers. And after 7, it starts to decrease once again. These numbers, you can check for yourself. They do add up to 1 if you add them all up. And this is the complete distribution of the sum of 2 dice rolls. Okay, and now a little bit of vocabulary. There's 2 kinds of variables, discrete and continuous. And discrete are the ones that this video is devoted to. Discrete variables are separate and unique values. And usually they're whole numbers, although that's not a requirement. But in the previous examples, they were whole numbers. When you roll a die, you can't get a 1.5 or any fraction of a number. It's going to be a whole number. And when you flip coins, you couldn't get a half of a head. So again, that's whole numbers only. And that's discrete variables. Continuous variables can be anything within a range of values. And We will study these at a future date. For example, your height is a continuous variable because measured accurately, your height could be anything within a whole range of values. Your height could be 165.1089, depending on how accurately you measure it. So your height does not have to be a whole number. It doesn't have to be anything. It's a whole range. But again, this video is all about discrete. So let's try another example of that. And back to rolling dice. Let's say you're going to roll over and over again until you see the first 6. And X is how many rolls it takes. Okay, let's find the distribution of X. So the first 6. Okay, so how is that going to happen? Well, it could happen on the very first roll. That's the quickest possible way it can happen. It could take 2 rolls. It could take 3 rolls. It could take 10 rolls. It could take 1,000,000 rolls. It's possible. So this is actually a situation where there's an infinite number of possible outcomes. But mathematically, it's going to be fine. Let's actually find these probabilities. So in order for X to equal 1, that means the very first roll has to be a 6. And that's the probability of a 6. So that's the probability of X being 1. The probability of X being 2, in order for the first 6 to happen on the second roll, that means you have to have a non-6 followed by a 6. So that's the probability that X equals 2. For X to be 3, so the first 6 is the third roll. That means you have to get 2 non-6s and then a 6. And that's the probability of that happening. In order for X to be 4, there has to be 3 non-6s followed by a 6. And for X to be 5, there has to be 4 non-6s followed by a 6. I think you see the pattern by now. And you could fill in the whole rest of the table. It would be infinitely long, but you could do it. And just want to make the point that these numbers, even though it's an infinite sum, they do add up to 1. Mathematically, you might recognize this. This is called a geometric sequence. And if you add up a geometric sequence, then you can get non-infinite answers. And specifically in this case, if you factor out the 1/6 and use this little mathematical trick here, then you can easily show that the numbers do add up to 1. Okay, moving on. So the distributions have to add up to 1, and that means there's a sort of an obvious, it seems like a simple trick, but it's very effective. Either A happens or A doesn't happen. And those two things have to add up to 1 because they are all possible outcomes. So if you want to find a probability that's difficult, you can do 1 minus the probability of it not happening. That might be easier to do. And the problems where you can exploit this are the ones where the words say the probability of at least one something happening or something. Let me do an example for you. Let's say you roll 5 dice and X is the number of 6s that you get. So it's possible to get anywhere from 0 to 5 6s. I want to find the probability of getting at least 1 6. So to get at least 1 6, you can get 1 6, 2 6s, 3 6s, anything. To do it directly, you would have to find 5 different probabilities, none of which are terribly easy. You have to find all 5 and add them up. That's doing it directly because it's 1 or higher, right? The other smarter way of doing this is to calculate the probability of getting 0 6s and then subtract that from 1 because all probabilities must add up to 1. So the other 5 probabilities are the same as 1 minus this one probability. Okay, so let's actually see how this works. Call that dice are independent. That means the probabilities will multiply up. So to get no 6s means not getting 6 5 times in a row. And that's the probability of that happening. So the probability of at least 1 6 will be 1 minus that answer that we just got. And it's actually, if you simplify the fraction, it's almost 60% chance of happening. But again, this is a trick that's really useful if you see the words at least one something happening. So you don't want to add up a whole bunch of different probabilities that you have to figure out. It's much easier to find one probability, the probability of 0 6s, and then do 1 minus that. And that's a useful little trick. Okay, so